DASSAULT Systèmes is a world leader in digital transformation, using collaborative software to integrate the whole manufacturing lifecycle from design to manufacture. As part of this overall aim, the Composites Research and Development Group are working to extend the tools provided by DASSAULT Systèmes, adding to existing design and analysis functionality the ability to handle measurement data from manufacture and feed it back into design and simulation arena. Automation of this process is essential if it is to fit into the timeframes of actual production processes. The industrial partners need to make the best use of their resources and cannot afford to have expensive machinery and staff idle while they wait for results to be processed. So, for DASSAULT Systèmes, the ZAero project is an opportunity to create an integrated solution for customers working in the composites domain. This solution ties together the work of the designer, analyst and production engineer. It manages the information flows and simplifies the decision-making process when manufacturing does not match design expectations. For the ZAero project, this has meant focusing on getting information from the as-manufactured parts and incorporating it into the simulations, so that the properties of the real-life part are calculated rather than the theoretical values based on a perfect as-designed part. DASSAULT Systèmes has worked with other partners in the consortium to define a standard format for storage and transfer of the composite design model, analysis results and measurements made during production. This has been formalized as a schema for a HDF5 format file, the manufacturing database. HDF5 is an open source hierarchical data format that supports large, complex, heterogeneous data. It is a standard, so it's easy for all partners to write software to access it. The ZAero partners supplying the measurement capability can write to the MDB the actual fiber directions, thickness, and anomalous features detected during layup. The features can be characterized as special types of defects. Information about the model stored in the MDB can guide the systems in how the measurement data should be stored. When measurement data from scanning or from sensors during information and cure is added to the MDB, event data is also added to allow tracking of the manufacturing process. The MDB can be monitored by each partner to detect when data has been added by other partners. For DS, this can trigger the process of defect data to determine the effects of defects on the structural performance of the component. A significant effort has been made to formulate methods to determine the effects of defects on the structural properties of the component. This is a complex problem, as the effects can depend on the location and the existing loads on the component. It may be that a defect is in an insignificant location, or maybe it's somewhere critical. To handle this issue, the tool needs to combine the properties of the defect, its size, orientation, type, within the stress field of its location. DS has developed a tool to do this in two ways, an empirical and an FE solution. The first is an empirical solution based on published research. This applies rules to each defect and calculates the change in stresses due to the presence of the defect. These changes are converted to a change in margin of safety at the defect location. This approach is fast as it simplifies the problem by making assumptions. For example, that the stress field is uniform and the layup is not changing in the area of the defect. We have shown that this method can handle thousands of defects in a few minutes, so it can work well within the time constraints of the production process. The second approach allows a more detailed approach. Here we generate a full 3D solid element model of the zone around the defect. In fact, two models are created, one with the defect, one without. Loads from the globe model of the whole structure are retrieved for the defect zone and applied as initial boundary conditions. Finer element analysis is carried out on these models, and comparison of the two models allows a measure of the change in safety margin. Typically, the second approach is used for defects highlighted as being concerned by the first method, or where the defect is large enough to have varying stresses or is in a zone of varying layup. The safety margin calculated for each defect are stored in the manufacturing database for later use by the decision control tools. Further work is needed to improve the empirical calculations and to extend them to cover more types of defect. The FE solution, and particularly the automatic 3D solid model generation, needs work to ensure robustness even in complex scenarios.